All right, friends and neighbors, welcome back to another networking video. It is now time for chapter 2 in our CCNA certification series, and this is the fundamentals of Ethernet LANs. Now, I'll just remind you that Ethernet lives at layer 1 and 2, so we're going to talk a little bit about both of those. And then on top of that, I'm going to include lots of stuff in the show notes about that, and so we're also going to reference these two books right here. These are the ones that I originally wrote for our networking classes, and they have Ethernet chapters in there. So there'll be a reference to those videos as well. Well, without further ado, let's jump into chapter 2. Now, I thought it might be kind of fun to do the "Did I know this already?" set of questions at the beginning of the chapter. Of course, I aced it, but there were a couple of tricky spots in there, and so let's do a reading from the book. All right, so question number 1. Some end-user devices connect to a LAN using a cable, while others use wireless. Absolutely true. Which answer best describes which devices use Ethernet to connect to the LAN? Now, the key here is that Ethernet is a wired technology. So the answer to that one, let me see, what letter was that? Only the end user devices that use cables are using Ethernet. Because if they were doing wireless, they'd be doing 802.11, and that is not Ethernet. Question number 2. Which of the following Ethernet standards defines the gigabit over UTP cabling? Well, we've got answers here of 10 G base T, 100 base T, 1000 base T, and none of the above. It's 1000 base T. 1000 base T is 1000 megabits, or 1 gigabit per second. Which of the following is true about Ethernet crossover cables for fast Ethernet? Pin 1 and 2 are reversed. I'm not even going to read all these. Pins 2 and 3 or pins 1 and 2 go to pins 3 and 6. So that was the answer there. I'll show you that in the pinouts later on in the chapter. Question number 4. Each answer lists 2 types of devices used in a 100 base T network. If these devices were connected using UTP cables, that's unshielded twisted pair, which pairs of devices would require a straight-through cable? This is actually pretty straightforward. Anything that acts like a PC needs a straight-through. So if you go PC to a switch, PC to a hub, router to a switch, those require straight-through cables. Anytime you're going to connect to a switch, or a router to a router, or a PC to a PC, you're going to use a crossover. Of course, today they auto-negotiate, but that's the answer to the question. What are the advantages of using multi-mode fiber? Well, the key to this one was that you had to realize what kinds of devices or what kinds of module used multi-mode versus single mode, and then also the distance thing. So the nice thing about fiber is that it goes longer than UTP, much longer. But you had to know also that multi-mode fiber uses an LED versus single mode, which often uses lasers, and so they switched up. They stuck those in there, so you got to be aware of that one. Which of the following is true of CSMA CD? Now, CSMA CD, if you didn't know, that is the carrier sense multiple access with collision detection. That's the access method. It's how Ethernet nodes decide whether or not it's okay to transmit. In CSMA CD, it doesn't prevent collisions, it just detects them, so collisions can happen. So that was the answer there. Which of the following is true about the frame check sequence? Well, it's all the way at the end of the frame. It's not a preamble or what we might call a header. It's a trailer. It goes at the end of the frame, and that is the frame check sequence. It's also a cyclical redundancy check 32, which makes it 4 bytes. Which of the following is true about the format of Ethernet addresses? Now, this was a little bit tricky as well. The OUI, or Organizational Unique ID, is in the front part of the MAC address. And again, I'll show you some examples later on, but it's the first 3 bytes. But you might also go, wait a minute, isn't that the first half? Well, you had to know, of course, that a MAC address is, well, 6 bytes long, and then the first half is 3 bytes, so it was a little tricky there. So if you whiffed on that one, I totally get it. Which of the following terms describe Ethernet addresses that can be used to send one frame that is delivered to multiple devices on a LAN? Now, there's 2 answers that were correct here, multicast and broadcast. There's actually 3 flavors of Ethernet or MAC address, the other one being unicast. Okay, That does it for our questions. So an overview of local area networks. So that's what a LAN is. And the smallest ones are SOHO, and then they move on up through SMBs, or small to medium-sized business, and then on to enterprise or campus. And so the components that we're going to be dealing with here are going to be hosts, right? And those hosts could be anything. They could be printers, they could be game consoles, they could even be IoT devices. Central nodes include things like switches and hubs, and then we connect to the rest of the world or another network via a router. But of course, any network today can have an access point in it, which provides wireless connectivity. Now, if you sort of drew a line down through this access point, right, just right in here, and then said anything on this side over here, this would all be Ethernet or 802.3, and then everything over here would be 802.11. Now, what's the difference between SOHO and enterprise scale? Well, it's really that, the scale. Enterprise networks just have more of everything. There are bigger concerns, right? We have to worry about redundancy and maybe additional security things. But no matter what kind of network you're working with, you are concerned about keeping your networks up and running, keeping them available. You are worried about security, you're worried about throughput, all of those things. But when you're dealing with an enterprise scale infrastructure, you have lots and lots of nodes, lots and lots of additional, I'll say, problems, lots of scaling issues, and you cover a lot of ground. So you have some additional issues. But it is, a lot of times it's wash, rinse, and repeat, right? You have more and more stuff to deal with, but the building blocks don't change. Now remember that we're talking about Ethernet. Now if we're going to say the standard name for Ethernet, it is 802.3. Now, if we go back in time, there have been lots and lots of different kinds of Ethernet standards. And this assumes that we're going to forget about all the other non-Ethernet standards. So even if we're just talking about Ethernet, there's been lots and lots of types of Ethernet. I've got a little note here about the DICS Ethernet. That's the DEC, or Digital Equipment Corporation, Intel, and Xerox version of Ethernet that was later codified into 802.3. So the 802.3x standard, or 802.3 2012, encompasses all of that. But what this means is that on any particular Ethernet network today, you can have a variety of standards and a variety of frames, which we'll see later on in this presentation. So there's been lots and lots of formats and lots of speeds. Today, we usually talk about, at least in terms of the copper-based standards, or the unshielded twisted pair copper standards, about 10 base T, 100 base T, and 1000 base T, or gigabit. Now, if you look on the back of a network interface cards, a lot of times it'll say 10/100/1000. That's what it's talking about, those three particular standards. And we have the ability to negotiate which speed we're going to use on a link. Now we'll talk more about unshielded twisted pair and fiber, but the basics of fiber go something like this. You have two flavors. You have multi-mode and single mode. Now mode in this case can refer to the color or wavelength or mode of the optics that you're using. Multi-mode fiber is usually got a larger core, and single mode, it's just a little tiny pinhole in there because it's designed for a particular wavelength. So multi-mode fiber doesn't usually go as far as single mode. Now, if you compare them to unshielded twisted pair, well, fiber is going to go longer. In some cases, all the way out to 30 kilometers or better. And a lot of times, the capacity of fiber optics is much greater than UTP, right? UTP has the fundamental limitations of an electrical signal running over copper. Okay, so some more details about unshielded twisted pair. Unshielded twisted pair is exactly what it sounds like. It is a set of wires put into a cable just like this one. And we terminate it with RJ45s. But inside this cable, there are 8 individual conductors. 4 pairs, each color-coded, right? So we've got the green and orange pairs. We have the blue and brown pairs. So there's 8 wires inside here, and it's unshielded twisted pair because the pairs are twisted. Now, in the early days, we only used two pairs for transmission. You can see those here. So these are the same ones that were cross when we talked about our crossover cable. So 1 and 2 and 3 and 6 go together, right? The orange and the green pairs. And when you do a straight through connection, it is exactly what it looks like on this side here. It is 1 goes to 1, 2 goes to 2, and so on. That's what most cables are when you look at them. But sometimes you need to use a crossover cable, and in those cases, we flop 1 and 2 to the positions of 3 and 6. So you can see that 1 goes to 3 and 2 goes to 6, and vice versa. So that's a crossover cable. Now you might ask yourself, well, what do we use the other pairs for? Well, if you have an older business or you have an older closet and you have some legacy gear in there, you might see that there's lots and lots of blue wiring in there. And these are the telco pairs. That left this other brown pair here for power over Ethernet. Okay, and that's a very traditional view, but today modern standards use these completely different. We use all 4 pairs for data. We can send power over all 4 pairs at the same time. It's kind of crazy. In addition, today we don't really use these telco pairs anymore because, well, most telephony is going to be either on your cell phones or on voice over IP, which runs over the data lines in your network. Now, each pair is twisted. They are twisted at different rates. So when I say that these pairs are twisted, if you imagine just pulling out the orange or the green pair, you would twist the wires together. And what that does is it reduces the impact of the electromagnetic fields set up by the signals or other surrounding signals. Now, in addition, the individual pairs are twisted at different rates. So in an inch, you might have 3 to 5 twists, and the pairs are twisted at a different rate, and the whole thing, this whole cable going down its length, is twisted again. So that's the really high-end sort of cable. And remember that almost all of these are included in 802.3 from the IEEE. Now, while we're talking about the IEEE, let's actually take a look at that website. So it's always nice to know where our standards come from. For the most part, in this particular course, we're going to be talking about standards from the IEEE, the Institute for Electronic and Electrical Engineers, and the IETF, the Internet Engineering Task Force. So you can actually go out to the IEEE site, right, IEEE.org, and you could be a member, right? There's student members, there's professional members, and you can look up all of these resources out here. Then you can take a look at, well, we might be talking about, right, the work group for, or the working groups for Ethernet. And this is the list of active projects in 802.3. So 802.3 is the Ethernet standard, and then there's a whole bunch of sub-standards or sub-working groups underneath that. But on top of this, we should recognize that we're talking about IEEE 802. And 802 is sort of all things networking. So for example, bridging was 802.1. And then you can browse the standards, of course, based on whatever you're interested in. And here are all the ones associated with the various groups. And there's 802.11, right, our wireless stuff. What does an actual standard look like? Well, if we were going to look at the document, it is all of the text and the descriptions, everything from the engineering and the mechanical specifications for this, the operational stuff, the framing, and everything else. Now they can get quite lengthy. You can see that now with everything added in, this particular standard is almost 4,000 pages long. For us, what we're concerned about right now is Section 3 of the 2012 standard. And this happens to be for gigabit Ethernet. But you can see that there are all of these sections. Now it's kind of small, so I won't belabor the point, but it's nice to know where the standards actually come from and that you can actually read these documents. Okay, so most of the time you're going to run into UTP and you're going to be running probably gigabit Ethernet. And that's layer 1. You might have fiber optics, right, if you're doing long runs, or you have connections between buildings. Okay, so that's all layer 1 stuff. What happens at layer 2? Well, the minute we move to layer 2, we have to start talking about frames. And in Ethernet, there are 2 kinds of frames that we want to become familiar with, at least in this introductory sort of chapter. And that is the original 802.3 frame and then the one that came from DICS. Now again, these are both in the 802.3 latest standard from 2012, but here is the formatting difference, right? So what we want to pay attention to is we start off with a preamble, and the preamble is just 101010. It's there to link up. But in 802.3 original, it's 7 bytes versus 8 for the Ethernet, what we call Ethernet type 2. That's how it shows up in Wireshark. And then we've got a 1 byte start frame delimiter here for 802.3. So it's just a variation in the binary pattern. The next thing that we can see in Wireshark, right, is the destination and source MAC addresses. These are 6 bytes each, and then we come to the type or the length. Now this is one of the big differences between these two frames. When you have 802.3, you get a length, which tells you, right, how much data you're carrying. Now that means that this necessitates an 802.2 header of 4 bytes, and in there it tells you what's going on. But Ethernet type 2, and we can see this in Wireshark, Ethernet type 2 gives us a type field, which tells us what we're carrying. And then we've got the variable length data fields, depending on which one you're using, and both use the CRC32 frame check sequence. Okay, so we have to realize that on the same Ethernet network, you might be running into 2 different kinds of frames. And here's what they look like in Wireshark. Here's an 802.3, and we can see that right here there's a length field. Now, significantly, all the length fields are going to be 1500 or less, which means that all of the Ethernet 2 type fields are going to be above those values. So if we look at 802.3, we've got this length field in here, but I don't know what I'm carrying. I don't know what's encapsulated. So we now have to have an 802.2 or logical link control header, which tells us what's going on. Now Ethernet type 2 is the exact opposite. Ethernet type 2 says, well, I'm carrying, in this case, ARP 0806, but now I don't know how long this is. So what I need to do is have either some very well-defined fields or an additional field later on that tells me how long this is or how much, the overall size. So there we go. That's what you can see in Ethernet is the difference between 802.3 and what we call Ethernet type 2. Now, something that is really important to understand is the different addressing that we have in Ethernet. Generally speaking, when we're talking about layer 2 or layer 3, we have broadcast, multicast, and unicast. And they're used in different areas. They have a dramatic impact on network capacity or network utilization and how they're used or who can see the traffic. So the first one that we have is a broadcast MAC address. Now I'm going to show you examples of each one of these here in a second. And the key difference is in the destination. All of the source MAC addresses in an Ethernet frame will always be unicast, but if the destination has all Fs in hexadecimal values in the destination, that means it's a broadcast frame. And this is going to go to everybody. So your networking devices have a particular set of rules that they use for handling broadcast traffic. Multicast traffic is similar. For IPv4, now we are talking about layer 2, and IPv4 and IPv6 are at layer 3, but this is our first hint that there's a tie between what goes on in layer 2 and layer 3. If this is IPv4, then the destination MAC address in multicast will be a 01. If it's IPv6, then the beginning of the MAC address at the destination will begin with 3333 right there. Okay? Now, multicast is specific to vendors or protocol or the type of transmission. If we're talking about point-to-point or unicast, right, one node talking to another node, the beginning part of the MAC address can be anything, as long as it's not FF01 or 3333. Now, it used to be that 00 was the reserved address beginning, right, the first byte for unicast addressing. We find out that that's not actually the case anymore, though we still see examples of that everywhere. And here are examples of each type. If we look all the way at the top here, right, we've got a unicast in the source and a unicast in the destination. This is a unicast transmission. The second one down here, frame number 1, is got a broadcast MAC address in the destination and a unicast source. This would go to everyone, and everyone would have to open it up and look at it. And then we've got a multicast destination down here. It begins with 0, 1 right there. Hopefully my head's not in the way. And then we've got a unicast source. So these are 3 different kinds of addressing that you would see. Now what we can also see right here when we look at the unicast is that Wireshark is trying to help us out, telling us that this is from an Intel machine or an Intel chipset. And that's also our indication that the first part of a MAC address is the vendor code or the OUI. So if we dive into those details, right, the MAC addresses have an OUI at the very beginning. And this is one of those tricky questions, or one of the tricky answers to the question. It's the first 3 bytes, but originally the first byte was reserved, right? So you might say whether it was 2. But today we're just going to remember that it is the first 3 bytes of a MAC address, or the first half of a MAC address, is the OUI. The second set of 3 bytes, the last 3 bytes, is the unique identifier for the NIC or interface. By the way, NIC is network interface card. And these addresses are burned in. And all that means is that the chips know what the MAC address is. But you still can change MAC addresses on many, many nodes. Okay. So if we think about that frame, right, we did preamble, we did all these addressing. That next thing was either a type or a length. If it's a type, then probably the most common ones you see, and there are 2 examples in the book chapter, are 0800, right? That means IPv4. 86DD, that's IPv6, and we saw 0806 for ARP. So this tells us, and this is how Wireshark decodes what's coming next. If it's less than 1501, this is a length field, and therefore is going to be really what we call the 802.3 style, and it has to have an 802.2 header inside in the data field. Finishing this off, right, we have a data field that follows. It's 46 to 1500 bytes of variable length. Now, again, if you've got an 802.2 header, it's a little bit less than that. And our frame check sequence is the cyclical redundancy check that's 32 bits long or 4 bytes. Now, this is a calculation. It's just a number. But the algorithm is CRC32. So to ensure that we're not going to transmit a frame in error, what we do is we transmit the frame and we calculate the CRC32, and then we put that number at the end of the frame. The receiver of the frame gets this, calculates the CRC32 again, compares the 2 numbers. If they're the same, then there's no error. Okay, half versus full duplex. So the chapter talks a little bit about this. If we go back to the original Ethernet, it was all half duplex because it was a bus topology. Everybody could hear what everybody else was doing. You just never know what you're going to run into. You never know if somebody put a hub in the network. You never know how fast things are going. You never know if auto negotiation is turned off. We want full duplex mode. We don't want to be in shared media. We don't want hubs. And so we want to negotiate to the best possible transmission speed and the best possible transmission mode. But half duplex means that only one side can transmit at a time. So it's kind of like having a conversation with somebody, right? I talk, then you talk, then I talk, then you talk. That's the way half duplex works. And we'll see here in a second why early Ethernet had to use a half duplex means. Full duplex means that both sides can transmit at the same time because we're using different pins to send those transmissions, right? I can send to you on one set of pins, you can send to me on another set of pins, and we can double our max theoretical throughput. But of course, to do this, you need a switch at the center. You can't have a hub. Now, it is possible to be switched and not full duplex for a number of reasons. It might be turned off. You might have a problem, or somebody might have stuck a hub in there somewhere in your switch topology. Now, this reminds me, let me show you a quick demo of something. So if we take a look here, I've got two topologies that look exactly the same. The only difference is the IP addresses. Now, this one here has a hub in the center, and this one here has a switch. So while they look the same, they're definitely not the same. So what I'm going to do is I'm going to tell this device, right, we've got it pinging. And maybe I'll stop that and just show you how I did it, right? So when we go to in Packet Tracer, I'm going to go to the desktop and I'm going to open up, we'll close that, there we go. I'm going to open up the command prompt so that I can issue a command. And this is the command that I'm doing. I'm going to ping from 1.3 to 1.2. And I'm going to turn on my simulation here so we can see what's going on. Okay. And what I'm interested in here is a couple of things. One is that Packet Tracer allows me to see the transmissions, but what happens when I get to this hub? When I get to the hub, it sends it to everybody that's connected. That's because a hub is shared media. And when you have shared media, you also have half duplex. So only one node can talk at a time. But the real important thing that we can see here is that when we have a hub in the topology, the transmissions are seen by everybody. It's kind of like a wired version of an access point. Okay, so we do not like hubs for a number of reasons in our topologies. So I'm going to stop this now. And I am going to open up, go back to real time here. Now I'm going to open up this node now. And we're going to do the exact same thing, but we are now going to have a switch in the center of the topology. So here we go to a continuous ping. And here goes our simulation. And we can see that the node sends it to the switch, but the switch only forwards it to the destination. And this is one of the fundamental differences and one of the huge benefits that we get by having switches in the topology. Only the intended recipient gets this transmission. And that is because the switch understands MAC addresses. And I will show that to you very quickly here. It's not really part of the chapter. But if I see the MAC address table, right here, it shows me that the switch has learned the MAC addresses and only forwards them to the destination, or the correct destination. Okay, so there's full and half duplex. Now, how does Ethernet operate when nodes are trying to send transmissions? Now, again, this is a little bit of a blast from the past. So what we call the access method is carrier sense multiple access with collision detection. And all that means is that carrier sense, okay, I am a node on the network and I'm going to listen to the network, right, on my receive lines to determine if somebody else is transmitting. If nobody else is transmitting, then I can transmit. However, in a shared media, where there's hubs, for example, I might cause a collision. There might be more than one node transmitting at the same time. In which case, that set of transmissions will actually collide somewhere on the network. The two voltage signals will hit each other and result in a spike in voltage and power. The collision detection part is the node's ability to see that spike and realize that their transmission just got hammered. So at this point, we've done the collision detection. Now we're going to back off. We're going to say, oh, geez, I just had a collision. I'm going to try again, and maybe try again, and try again, and try again. This is another reason why we get rid of hubs. But just because we don't have hubs doesn't mean that your switches aren't using CSMA CD. So we want to negotiate away from this. So in a perfect world, we would have switches, we would be running full duplex, and we would be running gigabit Ethernet to all of our nodes. But sometimes it's worth checking because you have performance or utilization issues in the network. Well, okay, that does it for chapter 2. It turns out this was kind of a short chapter. We got it done in one video. We were talking about layer 1 and layer 2. So big ideas for layer 1 were that we had unshielded twisted pair, we had some fiber optics, and then we had different ways to hook up our network. Some big ideas for layer 2, of course, were the framing, right? All of those fields in Ethernet, the addressing, the frame types, the two different kinds of Ethernet, 802.3 and Ethernet Type 2, and then how Ethernet operates, and of course that duplex operation and our ability to negotiate things. Well, like and subscribe for more networking goodness. Of course, we'll do chapter 3, so I'll include the look ahead for that. May those Ethernet frames always reach their destinations, and hey, this is certification and networking. You can do this.